Hi, welcome to this week 4 video. This will be about CAM process planning, how to maximize the manufacturing efficiency. We're going to see more theory about what is G-code and how it's generated and what tools we can use for G-code. And well, we're going to start with an introduction on the CAM process. Uh, this presentation aims to educate the audience about the CAM process planning and its important in manufacturing. We're going to talk about how G-code is generated, all the machines that are available, and how this works. And we're starting with what is the concept of G-code. G-code comes from geometric code, which is a program language used to program CNC machines or computer numerical control machines, and also 3D printers. In order to perform these operations and tasks using a CNC machine, the instructions needed to be provided in a machine understandable format. We can see that in this picture how the computer understands the movement on the CNC machine. We can see this code M107 will be the fan speed. The one below will be the nozzle speed without extrusion. On the right, we can see the layer height because this machine will go through different heights if it's necessary. We can also program the nozzle printing speed, the coordinates, which are one of the most important things when you use a CNC machine, and the extrusion length. These are some examples on how the G-code is generated and how it works. So we can see here we have G1 X coordinate, the Y coordinate, and an elevation. And it goes through, it goes to the other coordinate and different elevation, and this can be for any shape that you need it. And in order to generate this type of language for the machine, you usually need a G-code generator. What is a G-code generator? It's a tool that lets you generate the G-code, creating a full description on how to make something with the machine. We have certain types of G-code generators. For example, one will be a slicer that is used for 3D printing. 3D printing creates smooth and attractive parts because it uses a small nozzle to extrude thin layers of plastic usually. Even small part of a printed part can be hundreds of layers, and each with hundreds of small motions. This means on tens of thousands of lines of G-code. Each motion of the printer is given, for example, to trace the perimeter, crosshatch, to trace interior holes. And a slicer also takes into account the extrusion temperature, the fan, and speed requirements for running a particular material on your machine. After slicing the model, you can export the G-code if you have your 3D printer connected to your PC via cable or Wi-Fi. Then you can directly send the G-code file to the slicer to your machine. Another option will be to upload your G-code via USB, depending on your setup. Well, and CNC machining may take a different approach to manufacturing than 3D printing, but it can also get involved when cutting even a single pocket or through a hole. It takes several steps around the same path at increasing depth to make the complete feature. And even then, a finished cut removing the final layer of material is typically used to get the best surface finish. Other details that are hard to add by hand are tabs. These are bridges and breaks in the contours of the part to keep attached to the part material. A CNC router can add this easily, and automating the creation of multiple passes, finishes, and cuts. This is not necessarily the same for slicers. That maybe when you create these little bridges will be hard to program. And similar to 3D printing slicers, once you have everything set up for the code generation and the CNC router, the code generator has finalized the machining path. The G-code file can be generated and transferred into your CNC machine. Some code generators also provide the ability to simulate and see how the G-code is working, where the tool machining path or contour is simulated. This can be used as a premature check for tool collision or correctness for a generated code before the actual machining starts on the CNC machine. In these two pictures, we can see the 3D model of a slicer. And this will be done with a 3D printer, and we have all the bridges and these elements attached so it can print correctly, because it has hollow elements that are hard to print. And also on the right side we have how the simulation of the cut of this piece is working, and all these green contour lines will be the G-code or the path for the CNC machine. And let's take a look on how it works. Since CNC machines perform repetitive operations, the same basic cycle can be repeated. Let's take a look at some of the steps that go into creating G-code, which are automated by a G-code generator. And for 3D printing, the steps to generate the G-code will be after dividing an STL file into layers, the basic cycle for generating G-code for each layer will be, first of all, identify the outlines, both interior and exterior, determine how the infill will be laid with the interior of the layer, create an optimized transversal of the layer extrusion for outlines and infill, set the speed, extrusion temperatures, and fan speed, and then generate G and M codes to the start and end. Finally, convert the transversal path into GXS movements, adding extrusion E and feed rate F. An STL file is usually what 3D printers detect for 3D objects, so that will be the format for adding for any 3D printing software. And the following steps will be to prepare this STL file to generate the G-code to start printing. And for CNC machines, the parts needs to be milled and are similarly divided into depths, and a cycle is repeated at each layer. The steps will be to set the exterior or interior pockets or through holes. Second step will be set the depth of cutting and passing required to produce the full contour height. Then we have to set the tool diameter or curve. This will be the cutting diameter for a laser or plasma or water jet. Then we have to set the tool alignment to be inside or outside of the path. Then we have to set the spindle speed or cutting intensity. And then we create the G and M codes for the start and end. We have to create the positions of the path, including the multiple passes at depth to cut to create the full contour. And finally, we convert the geometry into GXS motions. Now let's talk about CAM process planning principles. First, we have to select the process. We have to choose the most suitable manufacture process based on different factors, such as material properties, geometric complexity, tolerances, and production requirements. This is crucial for ensuring that the manufacturing process aligns to the product specifications and delivers the desired outcome. For example, when manufacturing a metal component for a building, the process selection may involve choosing between casting, forging, or milling, based on the required strength, dimensional accuracy, and surface finish. The chosen process should be suitable for the material properties, let's say the ductility or hardness. And the geometric complexity will be for undercuts or thin walls of the component, as well as the production volume and budget constraints. Another principle will be the tool path generation. The creation of efficient tool paths is essential for optimizing material removal, minimizing tool wear, and ensuring the desired quality of the final product. A tool path generation involves determining the movement of the cutting tools during the machining process to achieve the desired shape and surface finish. Consider the scenario where a CNC milling machine is used to create complex shapes for building components from a solid block of metal. The tool path generation involves calculating the path of the cutting tool that must follow to remove the material from the block, creating the desired shape. Different tool path strategies such as contour milling, pocket milling, and ramping can be used to optimize the material removal, reduce the tool wear, and achieve the required surface finish and dimensional accuracy. Here we can see how the G code is generated for different heights, and the main purpose to generate this solid. Another principle will be the machine parameters. These parameters can be the cutting speed, the feed rates, the depth of the cut, among others. These are defined to maximize productivity while maintaining the quality and safety. And the proper selection of these parameters ensures an efficient material removal and reduce the risk of the tool to break. In the same CNC example, the parameters such as cutting speed, feed rate, depth of cut must be defined to ensure the efficient material removal and minimize the tool wear. For instance, a lower cutting speed and feed rate may be used for harder materials to reduce the risk of tool breakage, while a higher cutting speed and feed rate can be used for softer materials to improve productivity. Another principle will be the work holding and fixturing, how you're going to hold your material. Designing and selecting the appropriate holding devices and fixtures are crucial in ensuring the part of stability and accessibility during the machining. Work holding devices such as clamp, vices, and chucks secures the workpiece in place, while fixtures provide additional support and orientation. A proper work holding and fixturing can prevent part movement or deformation during the machining, ensuring the accuracy and consistency. On a milling machine, a suitable work holding device, that can be a clamp, would be used to secure the metal block during the machining. A custom fixture may be designed to provide additional support and orientation, ensuring that the workpiece remains stable and accessible for the cutting tool throughout the machining process. A proper work holding and fixturing help prevent part movement or deformation, which could result in inaccuracies and inconsistencies in the final component. Another important principle will be the machine selection. There are different types of machines for different types of materials. For example, if you're going to cut wood or a metal sheet, you will need a CNC. If you're going to generate a 3D object, maybe you need a 3D printer. Depending on the material, for 3D printers, you can do mostly plastic materials, PLA or maybe nylon, but also you can use different and stronger types of materials. Or another option will be if you're working with countertops or other types of elements, you can have a cutting machine for stone. And there is also another type of machine that will be the water jet, that water jets usually cuts almost all the types of materials. And while choosing the most appropriate machine tool involves considering factors such as capacity, accuracy, and functionality. This ensures that the selected machines can handle the project requirements and produce parts that meet the necessary specifications. The machine selection may also involve considerations such as the available floor space, budget, and integration with other equipment. To purchase this type of machines, you will need a space and budget also. And when planning the manufacturing of building components, selecting the appropriate machine tool is crucial for meeting the project requirements. For example, a large-scale building project may require a high-capacity CNC machine with multi-axis capabilities to produce large, complex components efficiently. In contrast, the small-scale project may only need a basic CNC milling machine or a manual machine to produce simple parts. The machine selection would also consider factors such as available floor space, budget, and integration with other equipment or automation systems. If you're a project manager, usually you will hire a contractor that already has the machine and gives you the service of cutting the material that you need. And well, for the CAM process planning practices, the first thing will be that we have to prepare our CAD model. First, we have to measure the elements on site. If we do have the elements on the BIM model, we can compare the measurements from the BIM model. But to be sure and to be precise, we have to measure the elements on the field. And then we go to the CAD model preparation. This step involves importing and preparing 3D CAD or 2D CAD models for CAM processing. Preparing the CAD model may include simplifying complex geometries and repairing any errors or gaps and scaling the model to the correct size. This ensures that the model is suitable for CAM processing accurately and represent the desired final product. For example, when preparing a CAD model for a custom steel bracket for CAM processing, the model may need to be modified by removing unnecessary details or features that don't contribute to the part's functionality. Any errors or gaps in the model should be repaired, and the model should be scaled in the correct size to ensure accurate machining. And a proper CAD model preparation ensures that the model is ready for efficient CAM processing and accurately represent the desired final product. On these pictures, what we can see is the measurements taken for a countertop for a bathroom. And well, these elements were cutted on a CNC machine for stone. And what you can see here is the detail on the cut. On this side has a miter edge. So that parameter needs to be prepared on the CAD model and to be defined so the machine can cut the stone on the miter edge. And that will apply for this piece and this other piece, so they can glue the material. Another practice will be to recognize the features of the element that you're going to cut. This practice involves identifying and extracting machinable features from the CAD model, such as holes, pockets, and surfaces. Feature recognition allows the CAM software to understand the geometry of the part and develop appropriate toolpaths and machining strategies for each feature. In the custom steel bracket example, feature recognition would involve identifying machinable features such as holes for fasteners, pockets for or weight reduction, and surfaces that require the specific finishes. By recognizing these features, the CAM software can automatically develop appropriate toolpaths and machining strategies to create each feature accurately and efficiently. And well, the process planning strategies also include developing step-by-step process sequencing operations and allocating the resource efficiently. This includes determining the order of the machine operations, how you're going to start cutting, in which ways you're going to cut, how many pieces you're going to have, also selecting the appropriate tools and machines, and planning for any required setup, change, or secondary process. An effective process planning ensures that the manufacturing process is streamlined and cost-effective. For a steel bracket, the process planning strategies would include determining the order of the machining operation, how you're going to drill the holes, the milling pockets, the finished surface, selecting the appropriate cutting tools and machines, and planning any required setup, change, or secondary processes. An effective process planning ensures that the manufacturing process is streamlined, cost-effective, and results on a high-quality product. What we're looking at this picture is an example of stone countertop that it was programmed and it was joined into all the pieces so you can glue the elements later. But you have to consider how you're going to cut the elements, where you're going to have the joints, the seam elements, and all the holes for the different accessories that comes on that countertop. For example, in that hole we have an accessory for Kohler K2214 sink, and the type of sink will be an overhang sink. So we have to configure the CNC to cut that hole appropriately for an overhang sink. Another practice will be the simulation and validation. Verifying the feasibility and efficiency of the process plan is crucial for avoiding any errors and inefficiencies during the production. A virtual simulation and testing can be used to identify potential issues such as tool collisions, excessive material removal, poor surface finish, allowing for adjustments to be made before the physical machine begins. This is important because once we start the process of fabrication, sometimes if we have any errors, we can lose the whole part and waste material. Before machining the custom steel bracket, a virtual simulation and testing should be performed to verify the process plan. And well, we will reduce the risk of errors and waste materials. Well, and the final step, the final practice will be the post-processing. This final step involves generating the machine-specific code. This can be the G code or the M code to control the CNC machines during the manufacturing process. Post-processing translates the CAM software's toolpaths and machining parameters into a format that the CNC machine can understand, ensuring that the machine accurately executes the planned operations. Once the process plan for all the material has been validated, the final step is to generate a machine-specific code that will control the CNC milling machine during the manufacturing process. In this picture, we can see the steps that we can follow and the role of the post-processor on a CAM workflow. First, we have that CAM converts the CAD to CL data. The post-processor converts CL data to G code, or the code that the machine uses, and the post tells the post processors that the G code dialect to target. That's basically how we can configure the machine so it can cut our material. Well, now we're going to see what software tools and platforms we can use for CAM design. The first software, I think I already mentioned it before, will be Autodesk Fusion 360. I believe this is one of the most complete softwares on the market. It is an integrated CAD/CAM and KE software developed by Autodesk. It offers a range of CAM tools for designing, simulating, manufacturing parts using different machine processing. These include milling, turning, and additive manufacturing. Fusion 360 supports a cloud-based collaboration, making it easy for teams to work together on projects. The Fusion 360 tool can enable the team to program CNC machines for various machining processes, such as milling, turning, and generate an optimized toolpath for efficient production. Well, another software will be Mastercam, that is a widely used CAM software. This was developed by CNC Software Inc. and provides a variety of tools for programming CNC machines. Mastercams feature an intuitive interface for and supports a wide range of CAD formats for seamless integration with different CAD systems. The other software will be Siemens NXCAM. And it's a comprehensive CAM solution developed by Siemens Digital Industries. It offers advanced programming capabilities for a wide range of machining processes, including milling, turning, and EDM. NXCAM supports multi-axis and multitasking machines, enabling the efficient production of complex parts. Another product from Autodesk will be PowerMill. That it's a high-speed and multi-axis CAM software developed by Autodesk. It's designed for manufacturing complex parts, molds, and dies using advanced machining techniques. This can be high-speed and 5-axis machining. And PowerMill provides tools for creating and optimizing toolpaths, as well as simulating and verifying machining processes to ensure accurate and efficient production. And another software example will be SprintCAM. That is a versatile and powerful CAM software developed by DP Technology Corp. It supports a wide range of machining processes, including milling, turning, wired EDM, and multitasking operations. And SprintCAM features an intuitive interface, advanced toolpath generation, and simulation capabilities, making it suitable for various industries and applications. An electronics manufacturer might use SprintCAM to program CNC machines or various machining processes for the production of custom electronic enclosures and components. SprintCAM's intuitive interface and advanced toolpath generation capabilities would allow the company to quickly and accurately program complex parts, improving productivity and reducing manufacturing lead times. The software simulation features would help ensure that the machining process is accurate and efficient, resulting in high-quality parts that meet the required specifications. Now we're going to see how we can integrate BIM with CAM data in process planning. About BIM and CAM data exchange, what we can do is we can convert BIM data into CAD models suitable for CAM processing. In order to utilize BIM data in CAM processes, the BIM model needs to be converted into CAD models that are compatible with the CAM software. This may involve exporting the BIM model in a suitable format such as IFC or DWG, and then importing this format into the CAM software for further processing and optimization. Well, it is important also that the BIM model it's checked and it is already measured to the exact dimensions that we need. One example will be an architectural firm design. They will design a building with complex facade elements, which include custom CNC machine components. The firm exports the BIM model as an IFC or DWG file, and this is imported into the CAM software. The CAM software converts the BIM data into the CAD model that is compatible with the CAM process, allowing the team to plan and optimize the machining operations for the custom components. Another example will be what we have in the picture. A structural designer at this section of this concrete element, and they already designed all the rebar shapes and dimensions inside the BIM model. The measurements are checked and all the dimensions and shapes are verified by the designer. So what we needed to do now to convert and to start the fabrication of these parts, we have to export this BIM model similar to the previous example. Maybe this can be on a DWG file, and then import that information into the CAM software. Once we got that on the CAM software, we go to the order in the machine to cut these shapes and generate these dimensions, and we will get the rebar shapes as we designed. And to ensure the consistency and accuracy of the geometric attributes between the BIM data and the CAM models, it is crucial to maintain this accuracy and consistency. This includes we have to verify the dimensions, the tolerances, so the team can compare the models, verify the dimensions, and other attributes that can match between these two models. If any discrepancy is identified, the team needs to resolve them before proceeding with the CAM process to avoid any errors and delays during the fabrication and construction. This review of the models, it's really important because once you use the machine and you start cutting, if you don't have the correct measurements, you will lose the material and have to start again. So that may lead to errors or maybe problems at the job site, and you will have delays or any issues on the fabrication. It's also important to implement open data exchange standards, such as an IFC standard when sharing the information and the COBie standards when this is handed to the facility management team. When you have a multidisciplinary construction project, different stakeholders, including architects, structural engineers, fabricators, collaborate using different software tools. To streamline this data exchange between BIM and CAM, the project team can implement IFC and COBie as their exchange standards. This will ensure that the project stakeholders can identify and can efficiently exchange the data. This will reduce the need for manual rework or custom data translators and improve the collaboration on the project lifecycle. Usually, the use of IFC will be for the construction phases, the execution, the planning phases, and the design. And the COBie standard will be for the project handover when the project is done, and for facility management when you want to identify any organize your elements in your building. When we use BIM software to the CAM process planning, well, the BIM data can provide valuable insights to inform and to show the CAM process planning. For example, we can see the material properties. We can visualize the geometric complexity and analyze the tolerances that we have. In the construction of a complex building facade, like the picture we're seeing, maybe we can have an organic shape. The BIM model can provide the information about the unique material properties and geometries of the custom design and cladding panels. And the CAD software can utilize this BIM data to select the most suitable machining processes, generate the optimal toolpaths, and determine the appropriate machining parameters. This integrated approach leads to improved manufacturing efficiency and higher quality of the final product. We can also incorporate the constructability, assembly, and installation constraints from a BIM model into the CAM process. BIM models can provide information of the constructability, assembly, and installation requirements for the building elements. By considering these constraints during the CAM process planning, potential issues can be identified and resolved before they cause delays or additional costs during the construction. This will help to ensure a smoother construction process and a higher quality final product. In a project involving the fabrication of large steel trusses for a sports stadium, the BIM model constraint is crucial information about the assembly and installation of the trusses. By incorporating these constraints and analysis with the CAM process planning, the fabrication team can ensure that the trusses are manufactured in a way that allows for an easy assembly and installation on site. This proactive approach helps to prevent potential issues and costly delays during the construction process. And coordinating the design changes and updates between the BIM and CAM models can ensure a smooth and efficient construction process. In a dynamic environment of construction projects, design changes and updates are inevitable, and this is crucial to maintain coordination between the BIM and CAM models and ensure that any change is accurately reflected in both systems. This synchronization enables the design and manufacturing teams to work and collaborate, reducing errors and improving the overall efficiency of the construction process. During the construction of a building, the design team maybe decides to change the building's structural system, and this change required the modification of the steel components that were already in the fabrication stage. By coordinating between the BIM and the CAM models, the design and manufacturing team can quickly and accurately update the CAM model to reflect the new design. This synchronization can ensure that the fabrication process can continue without any significant delays and errors. This can lead to a more efficient construction process. And in this picture, we can see the cloud platform that where the team can coordinate and communicate all these changes, and they can share all the updated files. Well, now we're going to see the significance of the CAM process planning in manufacturing to highlight the importance of the efficient manufacturing processes through the CAM process planning. Now we're going to see the steps that comes for CAM processing planning. And this will be the CAD-CAM process. Before will be the BIM model that it's converted to any CAD file. So we have the design idea on a CAD file and the geometry of the file. This includes the wireframe modeling and also maybe the surface. And well, then we have the computer-aided manufacturing. That will be the tooling selection machining condition, generating the tool path file. And another step will be the important step will be the program correction and verification. And once it is verified and corrected, we need to see for any toolpath errors or any tool collision and the geometry verification. Once we've done all these steps, we'll continue with the post-processing and we download the file into the NC program so we can use it on the CNC machine. Once we follow those steps, the machine will do the cutting of the geometry that we need. Or maybe this can be a 3D printer, or this can be a rebar cutting machine, or a steel cutting machine. And we'll have the final product so we can send it to our job site. This will be the steps. Also to talk again about the steps will be the product design and CAD modeling. This includes importing the information from the BIM model and verifying this. The second step will be the tool selection and toolpath generation. This includes what tools we're going to use, what will be the path of our CAM process. The third step will be the simulation and verification, where we can see all the errors or any detail that we have to adjust previously to approve this this process and send it to the machine. And the step 4 will be the post-processing and G-code generation. This is the step when we generate the G-code and we send it to the machine. In conclusion, we can say that the benefits of the CAM process planning will be the reduction of production time. The CAM process planning enables a faster and more efficient production process. We have an improved quality control. We can reduce risk and errors by verifying the simulations. We can also have cost savings with an efficient tool selection and toolpath. Among the reduced production time that will result in cost savings for manufacturers. We'll have an increased productivity by automating certain processes and optimizing the tool usage. The CAM process planning can lead to increased productivity and manufacturing. And we can have also the flexibility in design. The CAM process planning allows for more complex and integrated designs to be produced with ease. The challenges and limitations will be the complex geometries sometimes are difficult in creating toolpaths and simulating the machining processes. The machine capability is also one limitation that can restrict the tool selection process and affect the efficiency of the process. The material properties It's also one challenge. The different materials require different machines and machine parameters and different tools. That this can be a challenge on the CAM process planning. And last but not least, very important one will be the costs. The CAM software and equipment can be expensive, and you need a space, and you need to invest on a machine. So this will be a challenge for the small businesses with limited budgets. And well, what is the future for CAM and this process? Well, one will be to use artificial intelligence and machine learning in the CAM process planning. We can explore and use any AI algorithms to optimize the toolpath generation and automate the CAM process planning. There is also ways to improve the design with generative design, that the computer automatically with different parameters can generate different shapes. We can also talk about the adaptive CAM process planning that integrates real-time sensor data and feedback to adapt the CAM process planning to changing manufacturing conditions and improve accuracy. Mostly you can get the correct dimensions with different equipment. Another future direction will be the collaborative CAM process planning, where you can coordinate and develop a collaborative approach with the team to enhance communication and decision making, maybe using a cloud-based platform. And also having an integrated CAM and additive manufacturing, investigating the integration of CAM and additive manufacturing to optimize the manufacturing process and reduce waste. Well, and this will be all for this week. Let me know if you have any questions and any doubts and to clarify. And thank you for your attention. And we hope you understand the importance of CAM on the process planning in manufacturing and as manufacturing engineers and architects.